Welcome to Chemical Engineering Education. Today we are diving deep into vector and tensor operation, the mathematical foundation that power transport phenomena. Whether you are studying momentum transfer, heat transfer or mass transfer, understanding this concept is absolutely crucial for any chemical engineer. Let's get started. In this video, we will explore what tensor order really means, walk through example from scalar to higher order tensor, and most importantly, learn how to determine the order of result when we perform operation. This knowledge will transform how you approach transport. Chemical engineering relies heavily on continuum mechanics and field theory. Think about it when you are analyzing fluid flow, heat conduction or mass diffusion. You are dealing with quantities that have both magnitude and direction. That's where vector and tensor comes in. They provide the mathematical framework that bridges elegant mathematical formulation with real-world engineering problem solving. Understanding their component forms is essential for numerical solution and practical application. What is tensor order or rank? Now here is the definition of tensor order. The order or rank of a tensor refers to the number of indices or direction required to specify its components in a given coordinate system. It reflects how many directions are initially associated with the physical quantity the tensor represents. It also dictates how the quantity transforms under a change of coordinates, means rotation of axis. Now how to decide the order? Count the number of subscript or indices you need to uniquely identify a component of that quantity in a coordinate system. Alternatively, consider how many coordinate direction you need to specify to fully define its value, like ax. So here subscript is only 1 for a vector, and t sub xy for a trace tensor has that 2 subscript, means it is a second order tensor. Now order of zero tensor means scalar, so no directional dependence. So here is the definition. A scalar is a tensor of order 0. It has only magnitude. No indices are needed to specify its value. It is just a single number at each point in a space. It Its value doesn't change with a rotation of the coordinate system, like temperature, pressure, density, time and viscosity. Now order 1 tensor, that is vector, one directional dependence. So a vector is a tensor of order 1. It has both magnitude and direction. One index is needed to specify its component in a coordinate system like ax, ay and az. It transforms in specific way under the coordinate rotation, that is component mix. So example of vector in chemical engineering like velocity. So here v is nothing but vxi vyj plus vzk. So component here vx, vy and vz. Force, that f is fxi plus fyj plus fzk. So here fx, fy and fz are the components. Heat flux q, qxi, qyj, qzk. So qz, qy and qx all are component. And mass flux za. So zax, I, ZAYJ and ZAZ. So these are the component of a vector. Now order 2 tensor like second order tensor. So two directional dependence. Like a second order tensor is a tensor of order 2. It relates two direction or describe a directional quantity acting on a directed surface. Two indices are needed to specify its component in a coordinate system like Tij. So two indices are required to specify this tensor, and in 3D it has 3 squares, so 9 component. It transforms more complexly than a vector under coordinate rotation. Now example in chemical engineering field, viscous stress tensor, so that is second order tensor. Velocity gradient tensor, Nabla V, so that is also second order tensor. Rate of strain tensor, so anisotropic thermal conductivity tensor K. and identity tensor, that delta or I, dij, conical delta, all are second order tensor. Now coming to the higher order tensor beyond the common second order. So order 3 tensor has 3 indices like t, I, j, k. In 3D it has 27 component like 3 to the power 3. Example, the alternating unit tensor like or Levi Civita symbol epsilon ijk, that is used in definition of cross product and call. Even 4 order tensor is also there, so has 4 indices like that is t, I, j, k, l. So it has 81 component like elasticity tensor in a solid mechanics relating tests and strain for anisotropic material. So that has 4 order tensor. Now focus for transport phenomena. In introductory or intermediate chemical engineering transport phenomena, you will primarily work with zero order like scalar, order 1 vector and order 2 second order tensor. Higher order tensor appear in a specialized or advanced topic. So we will deal with in chemical engineering first order 0, order 1 and order 2 tensor. Now here is the classification of physical quantity. So we know that physical quantity we can classify 3 categories. One is scalar, vector and second order tensor, we already know. And how will you write scalar? That light face italic, vector bold Roman and second order tensor bold Greek. You can that way you can write scalar, vector and tensor. Parenthesis notation scalar. So you can write like that. So here third bracket vector result. So first bracket is scalar and brace means second order tensor result. Okay, we can write like using that notation. Now here if you multiply the two vector, two tensor or anything, so here if the sign is there, so in the order means the summation, the sum of the order of the multiplied quantity. So if there is a nothing is there, so you just do the summation. If that multiplication sign is there, so that will be so you have to in that sum you have to do -1. If dot is there, so after doing sum, so you have to do -2, and if that double dot is there, so you have to minus from the sum -4. I'll show you how to do that. Now here you can see here, so s and tau, so s is scalar and tau is the tensor. So this is scalar and this is so tensor. So scalar order is 0, tensor 2, so 0 plus 2, so 2. So v and w both are vector, so no sign in between. So vector order 1. Okay, so 1 plus 1 2. Similarly di and dj both are vector, or delta I delta j, so 1 plus 1, so 2. Now here v cross w, so v cross w, v cross w, so vector, so that is 1 and that is also 1. So now here, and if you see earlier, so when it is the multiplication sign, so from the summation you have to subtract -1. So here, so 1, then -1, then +1, so 1 1 that will cancel out 1, so it will be like a vector. So now when you multiply vector into vector, so that is actually vector. Now if you do that, I mean double multiplication or double dot, so now that sigma double dot tau, so this is a tensor, this is also tensor, and now because of this you have to -4, so that is 0, so it is like a scalar. So when you do that, so it is a scalar. Now sigma dot tau, so this is 2 for second order, tau second order, and because of this -2, so that is 2, so means it is a tensor. So I hope you know how to multiply, and after multiplication what or multiplication or doing in the operation, what will be the final quantity or final order. Based on that you can specify whether it is scalar, vector or tensor. So now here some algebraic laws for scalar, commutative laws. So RS, so that can be write as a SR. Associative law, so QR into S, so QR into RS. Distributed law, so S, that P plus Q plus R, so we can write SP, SQ, SR. These laws don't always apply for vector and tensor, remember that. So these laws for scalar, not for tensor and vector. Now here V minus W can be written as V minus W in that first bracket, third bracket and second brace. So all are valid. We can write in the vector. Scalar can be viewed as a zero order tensor, vector first order tensor, and tensor follow Bessel multiplication laws or rules involving dot, cross, and double dot. So this is double dot, that cross and dot. Now here general rule for tensor operation and order, already we did that. So again, so addition and subtraction, tensor can only be added or subtracted if they are same order. The result is a tensor of the same order, so vector plus vector, so that is vector. Example here, tau 1 tau 2, that is tensor second order and second order, so that will be second order. Okay, similarly for subtraction also, when you do the subtraction or addition, so things will not change, so same order. Now outer direct product or implied for juxtaposition. So the outer product two tensor vector and a vector forms a new tensor whose order is sum of the order of the original tensor. So vector into vector, your vector dyadic vector, so second order tensor, so order 1 plus 1, so that is 2. Now inner product, contraction or dot product. So inner product occurs when two tensor are multiplied and component sharing and index are sum. So that is called contracted. So each contraction sum over a repeated index reduce the total order by 2. So already I told, so if there is a dot, so summation will be minus 2. Okay, so here vector into vector dot product, so vector, so 1 and then 1 minus 2, so 0. Scalar, so vector dot vector, so that will be scalar. Okay, so vector dot second order tensor will be vector, so vector dot second order tensor tau, so that will be means 1, then 2, so this is 1, this is 2, and because of this, so minus 2, so that is 1, so that means vector. Next operation, scalar multiplied by a vector. Now multiplying a scalar phi by a vector is a straightforward component wise multiplication. So phi a, so it will, you can write like phi axi ayj and aj k. So we can write like that, phi axi, phi ayj, phi azk. Order analysis, so that scalar is 0 and that a original vector 1. So now no indices are summed or contracted, so it is like that, 0 plus 1, so 1 means vector. So the scalar merely scale each component of a vector. Now resulting order, so resulting order vector order 1, and that here 0 plus 1 I already told 1, so simply scaling doesn't change the tensor order. So like in chemical engineering example, heat flux for from temperature gradient, so q is equal to minus k del T. So here, so k thermal conductivity is a scalar, so that is 0, and del T the temperature gradient is a vector, so this is vector. So now 0 plus 1, so 1, so order is means scalar, sorry, vector. So q heat flux is a vector order 1. Now here vector and vector dot product. So the dot product of two vectors a dot b involve summing of the products of the corresponding component. Okay, so a and a into b, so that is ax bx plus ay by plus az bz. So we'll later we'll understand how actually happen. Now here if we do the analysis, so that order is 1, this order is 1, and this is for -2. So that will be, so 1 plus 1 minus 2, 0 means scalar. Okay. Now here that is I have already done that. So 1 1 minus 2 0. So here the example is conductive term v dot del t. Okay, so v is the velocity order 1 and del t is the vector order 1. So 1 and 1. So now and this because of this, okay, so dot is there, so -2 will be there. So because of that, if we do the operation, it will get the scalar. So del dot v dot del t is scalar order 0, representing the rate of temperature change due to convection. Now vector into vector cross product. So now that will result in a vector. So the cross product of two vector a cross b result in a new vector happen. Uh, so now operation vector cross vector, so that is cross product, so result in a vector. The cross product of two vector a cross b result in a new vector perpendicular to the plane containing a and b. So when we do that cross product, we will get the new vector. Now here that a original vector order 1 and again b original vector order 1. So now because of that cross, so we have to -1. So 1, so for that a cross b means 1, and this is 1, and because of this -1, so that will be 1 minus 1 plus 1, so that is 1. So it is a vector. Although there are multiplication, no indices are summed. Okay, that is contacted between a and b directly to the reduced order. The operation essentially construct a new set of component from the original one. The use of ijk introduce and then cancel indices. So here if you do that a cross b, so it is a vector. How? So that I already discussed. Now here vector uh, direct product. So now here the outer product of two vectors a and b forms a second order tensor. It is typically written by AB and A direct product B. So it will give that 9 component. Okay, so now here if you see that in between there is nothing, no sign is there. So vector A and B, so A vector order of A, that is 1, order of B, that is 1. Now as there is no sign, so 1 plus 1, so 2 means tensor. So there is no sum contacted indices between a and b. Instead, a new index is introduced or for each vector. So it is a nothing but a tensor. So I already talked about that. 1 plus 1, that is 2. So Reynolds trace tensor, that is rho v dash and v dash, both multiplication over the average. So this is also a second order tensor. Velocity gradient del v, or Nabla v. So Nabla is a vector and v is a vector. So there is a no sign. So 1 plus 1, so 2, that is tensor. Now another operation, vector tensor operation, inner product. So vector and second order tensor a dot t. Okay, so if I do that, one component summation of I a I dj. Now here that vector has original vector order is 1, tensor is 2. Okay, now dot is there, dot means -2. Okay, so now if we do that, so 1 minus 2 plus tensor 2, so that is 1, nothing but a vector. So that here resulting order vector order 1, order is 1 plus 2 minus 2, that is 1. So that is a vector. So less common as a direct physical term, but appears in a tensor multiplication or manipulation. Now here tensor dot vector inner product. So here if we do t dot a, so for that original tensor order is 2 and original vector order is 1. So our contraction occurred sum over index j. Now here, so result vector order 1. Okay, and if you do that, so a here, that is t dot a, t dot a, so order 2 and 1. Okay, because of this, so summation of minus 2, so 2 plus 1 minus 2, that is 1, nothing but vector or heat flux in anisotropic media. So q is equal to minus k del t. So here k is second order tensor order 2 and del t, that is 1. Because of the dot, so we have to do minus 2. So ultimately that dot product of this is nothing but a vector, means order 1. Now tensor operation. So tensor double dot b, okay, double dot product. So for that, so tensor order is 2, and because of double dot product, so you have to minus 4 we have to take. So 2 plus 2 minus 4, so that is 0. So that will give scalar. Okay, so that is the resulting, this result scalar order 0. So 2 plus 2 minus 2 minus 2, that is 0. So 2 plus 2 minus 4 is equal to 0. So that is the resulting order. So here viscous dissipation equation, so phi v tau double dot product del v. So here tau is second order tensor and del dot v, so this is vector and this is also vector, so that is order 2 tensor. So 2 plus 2, and because of this double dot product, so minus 4, so that is 0. So tau viscous stress tensor second order tensor, that Nabla v velocity gradient tensor is second order tensor, and phi v viscous distribution is a scalar order 0, so representing heat generation rate. Now operation involving the Nabla operator, so adding or reducing order. So now Nabla operator means I dou by dou x plus j dou by dou y plus k dou by dou z can be thought of as a vector operator or a tensor of order 1. So this is vector quantity, so order 1. When it comes order analysis, so Nabla into phi, so this is scalar and this is order 1, so nothing is there inside, so 1 plus 0, so 1 means vector. Okay, so vector order 1. Now divergence of a vector, so now here the del is a vector and then a is also vector, so that is order 1. This is also order 1. Because of this, so summation of minus 2, so 1 plus 1 minus 2 is 0, means scalar. Now next is del dot t, so this is vector, this is tensor, so order 1, this is 2, and because of this dot, so we have to take minus 2, so 1 plus 2 minus 2, that is 1, means scalar, sorry 1, 1 means vector. So here the order is 1, or a vector order, order 1 means a vector. Next is Laplacians of scalar. So here that Laplacian square phi means that Nabla dot Nabla phi. So here Nabla means vector order 1. So here Nabla again vector and phi is a scalar. Okay, and because of dot minus 2, so now 1 minus 2 and then plus 1, so that is 0, means scalar. So Nabla square phi or Laplacian of scalar is a scalar only, because 0 order tensor.